Good morning, folks.
Good morning. How are you?
Good morning.
Doing okay. Thank you for asking. We'll just take a couple seconds here to let some of your classmates get logged in. Okay. All right. So welcome back. Good morning, folks. Hope you've been staying warm with the chillier weather, and I hope you had a nice weekend. So we have lots to do here this week to get ready for exam 2 next week. However, I thought that this morning it would be helpful if we talk about how we calculate grades in this course. So what I'm going to do is start with an example of how your grade will be calculated in the course. I want to encourage each of you to please log into the laboratory portion of Wiley Plus, because we're going to use information from that website to help support your grade calculation. So if you can do that, please log into the lab portion of Wiley Plus at this time. Okay, so as you're doing that, I'm going to begin to share my screen with you. Okay, and so for calculating your course grade, I'm going to be using Microsoft Excel. If you have access to Microsoft Excel, feel free to join me in doing these calculations for yourselves. It's fairly straightforward if you have the software. If you don't have the software, you can still do it with pen and pencil, just a little bit more cumbersome without the support of the computer, okay? All right, so once again, please log in to Wiley Plus, the laboratory portion. We're going to need that for your homework grades. And if you have Microsoft Excel, bring that up onto your system. Okay, so I'm going to get started with that process. And so first we're going to do is just organize some information in the spreadsheet. The first thing is that we're going to document the exam and homework here. That will be column A. Column B is going to be the grades that you've gotten on an exam or homework assignments. Column C is going to be the weight of those activities, which I'm taking from the front page of your syllabus. And column D is going to be what I call the weighted score. Okay, so I'll explain all of this along the way. Okay, so we're going to have 4 columns of information. First column is going to be a listing of the exam or homework. Second column will be the grade you've earned. Third column will be the weight. Fourth column will be the weighted score. Okay, so in this course, you have three lecture exams. Oh, excuse me, lecture exam 1. Lecture exam 2. And lecture exam 3. You also have 3 lab exams. Lab exam 1, lab exam 2, lab exam 3. And of course, you have a whole bunch of homework that you've completed throughout the semester, okay? All right, so what I'm going to do next is put some hypothetical numbers into the grade column. I'm not using any individual person's grades. Of course, to figure out your grade, you would substitute your grades on exams and homework that you've gotten so far this semester, okay? So, all right, for lecture exam 1, I'll use some hypothetical numbers. I'm going to say that for lecture exam 1, myself as a hypothetical student scored 65%. So you put that in as a decimal percent. So rather than 65, you put 0.65 in. Okay. Lecture exam 2, you have not taken yet. So I'm going to skip that for the moment. Lecture exam 3, you also have not taken yet. Let's go down to lab exam 1. Okay. Lab exam 1. Let's say that your grade on lab exam 1 was a 59%. and let's say that your grade on lab exam 2 actually was a 68%. Okay, again, these are hypothetical scores. You would put in your actual scores. Okay, so for the homework, okay, if you have your Wiley Plus up on your computer, the laboratory portion that where you're given your lab homework assignments, okay, what I want you to do is in the Wiley Plus window on the website, go down to you see the grades tab. Go to the grades tab, right? GRADES. Go to the grades tab. It should bring up sort of a spreadsheet style report of your homework assignments that you've been completing through the semester, okay? And so what I'm going to ask you to do, there should be a scroll bar sort of at the bottom of that spreadsheet that you can scroll the whole way over to the right-hand side. Go over to the right-hand side of that spreadsheet in Wiley Plus. And let me ask you, I'm going to ask you a question in the chat window. Here we go. Here it comes. In Wiley Plus, in the grades tab along the far right, do you see a column labeled total? Okay. All right, great. I'm seeing that. Okay. All right. So thank you for participating. So folks, what I'm going to do at the end of the semester is take your total percentage. Your total percentage is going to be the points you've earned out of the points you've attempted on your homework, right? So the software is going to keep track of that for you. Okay, so let's continue here. So what I would say is when you're putting in your exam scores in the spreadsheet that I'm designing for you right now, we're going to be putting in your homework information. Okay, so many of you have very respectable homework scores at this point. So I'm going to say, you know, write down your total percentage in the homework from Wiley Plus, and I'm going to go back to my spreadsheet here. Hold on a sec. Okay, and so right now, I'm going to put in like a 97% as a homework score at this time. So to complete our calculation here, we've got to enter numbers for the exams that you haven't taken yet. Okay, we have to do that. And so first thing I'm going to do is color code these boxes yellow. So lecture exam 2, lecture exam 3, and lab exam 3. I'm color coding yellow. And what I'm going to tell you is that anything in yellow is going to be an estimate. Okay, anything in yellow is an estimate. Okay, that's the only way we can do this at this time, because you have not yet taken these exams. So I want you to think about how the semester is going for you, and I need you to put in what you feel is an honest, realistic estimate of the exam score you're going to earn on lecture exam 2. Okay, so let's say, you know, you've been thinking about your grades in the course, you've gone to a tutor, you're working real hard. So let's see what would happen if you got a 70% on lecture exam 2. For lecture exam 3, which is the final exam, okay, you need to do the same thing. For the final exam, you're going to be all done with lab, so you won't have to worry with lab anymore. So maybe that gives you a little bit of extra time to focus on the lecture. So let's see what a 75% in lecture exam 3 would get you. Lab exam 3, of course, is coming up as our final exam in lab for the semester. So we'll say here, let's say for lab exam 3, you end up with a 72%. Okay, So you put in your grades that you've earned so far. You put in your homework percentage from Wiley Plus that you've earned so far. And then in the spreadsheet cells that are color-coded yellow, you type in what you think you can get, okay? Because, you know, this is an estimate at this point of time. All right. So for the weights, column C of the spreadsheet, for the weights, those weights are defined on the front page of your syllabus, okay? So I have them here for you. You don't have to pull your syllabus up unless you want to. But lecture exam 1 is weighted at 13%, so that's 0.13. Lecture exam 2 is weighted at 16%. Lecture exam 3 is weighted at 14%, okay? All right, lab exam 1 is weighted at 13%. Lab exam 2 is weighted at 15%. Lab exam 3 is weighted at 15%. Okay, and the homework, all the homework that you've done this semester and you will by the end of the semester will be weighted in your final course grade as 14%, okay? 14%. All right, so those are the weights, again, you take from your syllabus. In column D, we need to calculate the weighted score. So the weighted score is going to be as follows. You're going to take the value you have in column B and multiply it by the weight in column C. So for example, I'm going to hit in the spreadsheet with cell D2 selected, I'm going to hit the equal key. I'm going to hit 0.65 here, and then I'm going to hit the multiplication key on my keyboard, the asterisk key. Then I'm going to hit 0.13 in the spreadsheet. So I have cell B2 times cell C2, and I'm going to hit enter, and it's going to give me a weighted score. Okay. I'm going to do the same thing for every corresponding element in columns B and C. For those that are familiar with Excel, all you have to do is go up to the cell we've just calculated. In the bottom right corner, there's a tiny little green rectangle. I'm going to select that with the left button of my mouse. I'm going to hold on to it, and I'm going to drag it down. And the computer is going to be intelligent enough to do all those corresponding calculations for me. Now, to calculate your total grade at this time, okay, what I'm going to do is hit equal here, and I'm going to add all the weighted scores up. So that would be sum. I'm going to sum them all up and hit return. And there you can see that my final course grade is, if these were my actual grades, my final course grade would be a 72.4%. Okay, so this is my final course grade. Okay, so obviously the numbers before you are hypothetical numbers. I'm not putting your numbers in. You should put your personal numbers in at home when you do this kind of calculation. But this is the process that I will follow to calculate your grades at the end of the term. Okay. All right. So folks, do you have any questions?
A quick question.
Go ahead.
So that we have 3 exams left, and like, let's say we just did this and we have to get at least an 85 to pass. Like, is it even worth continuing, or should we just like withdraw from the class?
Well, that's a hard decision, right? And it's something that I can't make for you. What I'm saying is this: if you feel personally that you're not going to pass, if you think, well, I just can't do this, then that's probably true. You probably can't do it. And if that's how you feel about things, but you have the inclination that you still want to repeat the course in the future because you really want to get to be a nurse, or you want to go down that career path that you're in, then I would recommend that I would recommend you withdraw from the course, but you continue to come to class so that you get exposed to the content of the course in the final third of the semester, so that the next time you repeat the course, you're not shocked by anything that you haven't seen. Okay. All right. So that's a tough one.
Another quick question. I thought that passing, because I read everywhere that you have to have at least a C or higher. So not an 85, but a C or higher, I thought.
Yeah, no, I think you're misunderstanding. Passing for the course is a C or higher. I think what Rochelle was asking about is if she needs to get an 85 on one single exam. Okay.
Oh, okay. Yeah, I'm so sorry about that. I misunderstood.
Okay, that's okay. Okay. So very hard decisions for some of you coming up. I appreciate that. And I would encourage you to not only come talk to me, but talk to tutors. And I would also encourage you to talk to people that love you and care about you, such as your parents, such as your spouses. Tell them what's going on and think about where your future is, where you want it to be. For some of you, the right decision is going to be withdrawing and repeating the course, without a doubt. Okay. For others, you might be very close that if you can bolster your effort here at the end of the semester, you can squeak across the line and actually earn a C in the course and move on to AMP2. It's a very individual decision that you need to, you need to spend some time thinking about. Okay. All right. Any other questions about how I'm going to calculate your grades at the end of the semester? Okay. So if the method I'm using to calculate your grade, if you're not able to repeat this for yourself with your own scores, I would be more than willing to help you with this during office hours to let you know, where you stand and help you make that decision for yourself. Okay. So please come visit with me if you want my assistance with this. But what I've shown you this morning is exactly what I'll do to calculate your course grade. Any final questions? Okay, gang. All right. Okay, so there you have it. And please let me know how I can support you in your decision-making process. Okay. So let's continue here. We do have to get started in chapter 10, but before we do that, I want to go back and finish off a little activity from chapter 9. Remember chapter 9, we were talking about the angular rotation terms, and we defined a whole bunch of them in your notes from last time. And so what I'd like to do is get you up and moving this morning, okay? Get you up and moving this morning. This is not something we typically do, but I'll ask if you please indulge me a little bit. Okay, I'm talking about the terms you can see in, say, figures 9.5, 9.6, 9.7 of chapter 9. Okay, and so I'd ask you to stand up wherever you are right now, at home or at the office or wherever you are in school. Stand up, get beside your desk, and let's do some of these motions together. Okay, let's do them together as a group and see how they turn out. So this is meant to be a lighthearted, fun activity. I don't want you to hurt yourself, which is to say that I'm going to ask you to do some things where you might lose your balance. And so be sure you're close enough to a table or a wall that you can balance yourself while we're doing these activities together, okay? So to do this activity, the next activity, I'm going to have to turn because I'm really cramped in my office space. I'm going to turn this way. So if you're standing up, go ahead and stand up, get yourself into a comfortable anatomical position, and let's do some of these motions together. And I want to encourage you during your study time to do these motions at home. So not only do you gain an intellectual awareness of what the motion is, but you can actually feel it, okay?
Excuse
right,
me, Professor
so-
Todd. Are we supposed to be able to see you?
Can you not see me at this time?
I can't see you. Maybe it's just me, but I
Oh.
can't see you.
All right, hold on a second.
I see your screensaver.
Right. Okay, let's
Yeah,
try
we don't see you
this.
either.
Can you see me now?
I can see you now.
Okay, can everybody see me?
Yeah.
I
Okay,
can see you.
all right, great. Thank you for the feedback. All right, so let's stand up, get into anatomical position. What I'm going to ask you to do next, I'm going to take these things slowly. I'll just tell you one thing, ask you to do it, and try your best to hold that position without falling over, okay? So the first thing I'd like you to do, I would like you to hyperextend your right hip. Hyperextend your right hip. So I know you can't see the lower half of me. I just don't have enough space in my office to show you that. But what you should be doing right now is that your right leg should be behind most of your body, right? And you should feel sort of a stretching sensation in your lower back, maybe your buttock a little bit, even the back of your thigh. So you are hyperextending your right hip at this time. Now, with the right hip hyperextended, I want you to flex your right knee. Okay, so flex your right knee. So that means your right leg is behind your body and your knee is bent with your foot coming towards your behind. Now hold that position if you can. Now with your right hip hyperextended and your right knee flexed, I want you to additionally plantar flex your right ankle. That means you're going to point your toes. You're going to point your toes in addition to the other two motions you've done. Right hip hyperextended, right knee flexed, and the right ankle plantar flexed. You're pointing your toes. Hold it for a count of 3. 1, 2, 3, and relax. Put your leg down, shake it out a little bit. Relax, get into anatomical position again, okay? So let me just ask in the chat window. Here we go. Were you successful? Because I can't see it, folks. I don't know. Could you feel your muscles stretching? All right. All right, so let's do another one together. Okay, what I'm going to ask you to do is get into anatomical position. Once you're in anatomical position, I'd like you to raise your arms out straight in front of you. Raise your arms out straight in front of you, okay? Now, what I'd like you to do next, I'd like you to flex your elbows so you form roughly a 90-degree, a right angle with your elbow. Okay, so we have our elbows flexed. Now what I would like you to do is to pronate your palms. Pronate your palms means you rotate your thumb towards the midline. So we're going to pronate now. And now our palms are facing away from our face. Okay, sorry, my video camera is cutting out there. So we've just pronated our palms. Now what I would like you to do with your palms facing away from your face, I would like you to ABD, abduct your fingers. So when you abduct your fingers, you spread them apart, right? You do this. Abduct your fingers, okay? And hold it, 1, 2, 3, and relax. Go ahead, put your arms down and just relax. Okay, let's do another one. Let's start from anatomical position. Make yourself comfortable, anatomical position. What I'd like you to do next, I would like you to flex your left knee. Flex your left knee, not your hip, your knee. Flex your left knee. So right now, your knee is bent and your foot is behind your body, but your thigh is still in anatomical position because you're not changing the angle of your hip. So you flexed your left knee, stay in that position. Now what I want you to do with the left knee flexed, I now want you to flex your left hip. Flex your left hip. So if you're going to flex your left hip, your thigh is going to come out in front of you. So your thigh is anterior. It is forward of the rest of your body, and your knee is bent. Try to hold that position. Now with your left hip flexed, I want you to dorsiflex. Dorsiflex your left ankle. That means your toes are going to be pointed towards the ceiling, So you should be feeling your gastrocnemius muscle and the lower leg stretching. So with the left knee flexed and the left hip flexed and the left ankle dorsiflexed, if you have space in your environment, what I want you to do next, I want you to extend your left knee. Extend your left knee. So you're straightening your leg out, right? But you're still dorsiflexing. Hold it. 1, 2, 3, and relax, and relax. Go back to anatomical position. Okay. All right, folks. We'll do one more. Let's get into anatomical position. What I want you to do is, in anatomical position, I want you to add, ADD, adduct, ADD, adduct your shoulder blades. To adduct your shoulder blades, that means you need to move them towards the midline. So that means you're going to push your chest out and your shoulder blades are going to get closer to your vertebral column. So you're pushing your chest out right now. So hold that position. Next, I want you to protract your head. Protract your head means you need to move it forward in the transverse plane, right? So it's the chicken head motion. Here we go. I'm going to protract. I'm sticking my head forward while my shoulder blades are adducted. Boy, you can really start to feel the muscles in your shoulder and neck stretch. So with your head protracted, I want you to do the following. Protract your mandible. So your head's protracted. Now I want you to extend your mandible forward. Go ahead, protract your mandible. You're going to look odd. I look odd. Now with your mandible protracted, I want you to depress your mandible. Depress your mandible, which means you open your mandible, you open your mouth. Why don't we look like aliens? Hold it. 1, 2, 3, and relax. And relax. Okay, folks. To help shake it out here, because that's the last one we're going to do. If you want to just kind of relax a little bit, circumduct your shoulders posteriorly. So in other words, do the shoulder rolls. That'll help get the kinks out. Do the shoulder rolls. Okay. All righty. Okay, folks. Thanks for participating. I hope you enjoyed that, and I hope you felt the sensations of doing some of these motions. I really want to encourage you to do that during your private study time. So hopefully that gets the blood flowing a little bit, and we're ready to rock and roll in chapter 10. Go ahead and make yourself comfortable at home. Go ahead and take a seat. And let's get started in chapter 10, okay? Okay, so do you have any questions before we begin? Okay, all right, gang. So I'm going to move quite briskly. I anticipate that we're going to spend the rest of the day at chapter 10. Wednesday is going to be chapter 10 during lecture, and I anticipate probably needing to use some of lab time on Wednesday to finish our coverage of chapter 10 so you're ready for your exam, okay? Because there's a lot to do here, but we can make it happen. And so here we go. Chapter 10 is muscles, right? So you've all become an expert at identifying major skeletal muscles of the body. but we really haven't talked about the physiology of muscle tissue, and that's what chapter 10 is about. So let me just start with some opening talking points here. All right, first off, the word myology. Myology is a scientific study of muscle. If we think about what muscles do, if we think about what muscle tissue tries to accomplish, there are many things that it does, but there's one really big important idea about the function of muscle tissue. The function of muscle tissue is to take chemical energy that exists inside the muscle cell and use it in such a way to manufacture mechanical energy that can then be used to tug on something like a bone, to move the skeleton, or to squeeze a structure shut to prevent the loss of liquid out of that structure, such as your urinary bladder, right? Sphincter muscles in the urinary bladder intentionally close shut to prevent urine leaking out of your bladder when you don't want it to leak out of your bladder, right? I mean, babies don't have that ability yet. Their muscles need to mature and they need to train their body to do that. But you and I now take it for granted because we've been doing it for so many years. The function of muscle tissue is to transform, make this just a little bit bigger. Function of muscle tissue is to transform chemical energy into mechanical energy for the purpose of generating force to perform work, like moving a bone. Okay, that's the big deal about muscle tissue. Okay, there are other functions of muscle tissue. Additionally, muscle tissue works to stabilize body position, right? Think about how your muscles had to contract and strain themselves at times so that you could do the motions we just did, right? So you had to maintain your body position so you wouldn't fall over. Or if you're sitting up in the chair, you don't fall over in the chair. A newborn infant, right, often cannot lift his or her head because their muscles are not developed enough in the neck and shoulder region. So muscles will stabilize body position. They will regulate organ volume. Again, I use the urinary bladder as an example so that we do not pee ourselves. Okay. Additionally, generate heat, right? Muscle contraction is going to generate heat. And that heat is going to be used to maintain our body temperatures, thermogenesis. And finally, muscle contraction is also used to actually move food and drink through our GI tract, through our gastrointestinal tract. Okay. All right. So, you know, you chew on a cheeseburger, you take a bite of cheeseburger, you chew it, you swallow it. That cheeseburger will go down your esophagus into your stomach. Well, it doesn't just fall. I mean, gravity is helpful, but in addition to gravity, the smooth muscle tissue that lines the circumference of the esophageal tube is going to contract in a rhythmic manner to push the food down into your stomach. That rhythmic contraction of muscle tissue has a special name. It is called peristalsis. Peristalsis. Okay. All right, folks. So those are just some opening points. I'm next going to shift back to a quick description of the different types of muscle tissue in the body. And this should not be a surprise to you because you're all experts on it from chapter 4. right? We know we have skeletal muscle tissue. Skeletal muscle tissue. Most skeletal muscle tissue of the body is responsible for moving the bones of the skeleton. Not all skeletal muscle. For example, your tongue is a skeletal muscle, and so your tongue doesn't really move any bone, it moves itself, right? The diaphragm, which is the separation of your thoracic and abdominal cavities, the diaphragm also is a skeletal muscle, and that by and large itself does not move bone. Okay, so while most skeletal muscles move bone, there are a couple notable exceptions to that. Okay, you know that skeletal muscle is striated. Okay, we've talked about that before. Okay, we know that skeletal muscle contraction is voluntary, which is to say that your conscious mind can control it, right? You were doing those activities with me, and so we were moving our skeleton in various ways by contracting and relaxing different muscles. You can think it and your body responds, okay? Is under voluntary conscious control. Okay, and it's important that you appreciate that skeletal muscle tissue is coordinated and regulated both by the nervous system and the endocrine system. Okay, we'll get much more about the nervous system in this chapter and in future chapters of AMP1. You won't get a lot of endocrine knowledge yet until you get to AMP2. Okay, next we have cardiac muscle tissue. Cardiac muscle tissue forms most of the heart wall mass. Okay, so most of what the heart wall is cardiac muscle tissue. Okay, cardiac muscle tissue is also striated, although the striations do look a little bit different from the skeletal muscle. The heart itself has the ability to contract and beat independent of the nervous system. And that's because there's a subset of cells in the right atrium called pacemaker cells that help generate the rhythm of the heart contraction. That property is known as autorhythmicity. The heart has the ability to contract without nervous system stimulation. This characteristic is known as autorhythmicity, right? That's a big word there, autorhythmicity. Excuse me. Okay. You'll learn more about that in AMP2. In AMP2, you're going to do a whole chapter on cardiovascular circulation. Finally, it's also important that while the heart does have the ability to beat independent of the nervous system, both the nervous systems and endocrine systems can influence the heart functionality and the heart behavior. Okay, I mean, just think about it, right? You get scared, all of a sudden adrenaline is released, right? Epinephrine, and boom, your heart rate goes sky high, right? So you know from your own personal experience that that must be true. Finally, we have smooth muscle tissue. A smooth muscle tissue is not striated. Smooth muscle tissue is found throughout the body. Let me give you a couple common places. Okay, it's found in the walls of blood vessels. Found in the walls of the tubing of the GI tract, right? The esophagus, parts of the stomach, Small intestine, large intestine, all of that anatomy has a large quantity of smooth muscle tissue in the wall of the anatomy itself. Okay, you're also going to find smooth muscle tissue in organs that regulate liquids and control their motion. So you're going to find a lot of smooth muscle tissue in the urinary bladder. Okay, you're going to find a lot of smooth muscle tissue in the stomach, because obviously you're not only eating food, but you're drinking liquids, and so those liquids have to have their motion controlled and coordinated properly. Okay, you're going to find smooth muscle tissue around the follicles that are embedded in the dermal layer of your skin, right? And so that helps give you goose pimples when you get cold or scared. Okay, so there's just a whole bunch of locations where smooth muscle tissue is found. Let's go back up here. I should have mentioned for the heart that the heart is involuntary. Okay, you cannot consciously control your heartbeat. And the same is going to be true of smooth muscle tissue. Smooth muscle tissue is also involuntary. Okay, you cannot sit there with your mind and ask the smooth muscle tissue in your esophagus to simply constrict. The body will just ignore the thought that you've had. It won't actually comply, right? So smooth muscle tissue is involuntary. All right, so that's just a quick refresher of the three major types of muscle tissues we find throughout our body. Let's take a look at the properties of muscle tissue. For those that are following along in your textbook, now there's some key information that I'm listing out in your notes from the first 2 or 3 pages of the chapter. In my textbook, which again is a physical book, I'm looking at information on pages 306 and 307. Okay, the first property of muscle tissue is that muscle tissue is electrically excitable. Okay. Okay. There's a lot of nuance to this this talking point, which we will get into in deeper conversations probably on Wednesday and for the remainder of the semester. But suffice it to say that both neurons of the nervous system and certain specialized muscle cells in the heart have the ability to generate what's known as action potentials. Action potentials are special electrical signals that can be created and propagated along the plasma membrane of certain types of cells. These signals can be propagated along neurons and muscle cells. So that's a property of muscle tissue. Muscle tissue can generate and propagate electrical signals called action potentials. Okay. And I'll put down here in your notes that only neurons of the nervous system and specialized cardiac muscle cells in the heart have the ability to create these electrical signals. And so I'll say one thing now and I'll leave it rest for later conversation. There is a difference. There is a difference between creating an electric signal and allowing the electrical signal to spread across the surface. There is a difference, okay? So neurons can create electrical signals and they can allow the signal to spread. All muscle fibers of the body can allow electrical signals to spread, but only a subset of specialized heart cells can actually create the muscle electrical signal. Okay. All right. Let's continue. So muscle tissue does have some interesting electrical properties. Second feature of muscle tissue, contractility. Muscle fibers have the ability to forcefully contract. That contraction usually is associated with shortening of the fiber, right? When you shorten the fiber, you're going to tug on something like a bone and move that bone, move that limb, whatever it is that the muscle is tugging on. Okay. You certainly could have a scenario where the muscle contracts, and because the object is trying to pull on is too loaded down with weight, such as when you're weightlifting at the gym, the contraction really doesn't lead to a shortening, and it doesn't lead to a movement of an object because the barbell is just too doggone heavy, right? So, okay. Third property, extensibility. By extensibility, I mean that the muscle's tissue has the ability to stretch. You felt that today when we were doing some of your leg work, and you could feel maybe your hamstrings or your gastrocnemius muscles in your legs stretching. Finally, the fourth property of muscle tissue is elasticity. Elasticity. Elasticity refers to the ability of a muscle fiber to elongate, which is to stretch, and then when you relax the tissue, it has the ability to go back to its normal, natural, unstretched size. That's elasticity, like the elasticity of a rubber band. You stretch it out, then you let one end go, and it just goes back to its normal size, its normal diameter and dimensions. Okay. So typically, you know, when you're doing weight-bearing activities at the gym, as long as you're not going to ridiculous extremes and actually physically harming yourself, right? You want to lift enough weight so that it's challenging but not insane. And by doing that, you're literally producing minor tears in the muscle fibers that then when you go to sleep at night, your muscle tissue will repair those tears and will build other things that I'll talk about in about 10 minutes to make you stronger from having done the exercise that you've just attempted. Okay, folks, please stop me with questions along the way if you have them. I'm going to keep moving here. We need to talk about some of the connective tissue that's associated with skeletal muscle. So let's take a look at figure 10.1. And I'm going to ask it, you know, if you have figure 10.1 open in front of you, that you look at these things as I point them out. So first, a couple things to remember. We know that a muscle cell is also known as a muscle fiber, which is also known as a myocyte. Those three terms are synonymous. Remember that a muscle cell equals a muscle fiber, which equals a myocyte. Okay. Now, we need to talk about the fascia that's around the muscle, but you may not remember what fascia is. So let me define fascia for you. Remember that fascia, F-A-S-C-I-A, fascia, refers to a sheet of dense irregular connective tissue that lines body walls and surrounds muscles and other organs to stabilize them. Okay, think about all the internal organs you have in your abdomen. Think about when you're running a race or playing baseball or dancing or doing gymnastics, and how all those internal organs could move around and slosh around, right? If they move around and slosh around too much, too violently, they will actually rub up against each other, slam into each other, and damage each other. So Mother Nature has created an ingenious layer of fascia, of membranes, of connective tissues that wrap around structures and help hold them into position so our bodies don't damage themselves as we move around. So this is what I'm talking about, okay? Muscle tissue is no different, right? It's going to move, it's going to contract and so forth. We want to be sure that it basically stays in its intended location and does not slip off the bone, okay? So let's take a look at the various types of connective tissue here associated with skeletal muscle. Okay, first we have the epimysium. Epimysium, if you're at figure 10.1, look along the right-hand side column of terms from the top to down. Epimysium is the third term down on the right side. It's also the fifth term down because the image is showing you the same structure from different perspectives. Epimysium is the outermost layer of fascia that surrounds the entire muscle. Okay. Next, we're going to have a slightly deeper layer of fascia. This is called the paramysium. Paramysium, as you look at the terms in figure 10.1, is the fourth term down on the right side from top to bottom, fourth term down. And also the seventh term down as well. Paramysium is the layer of fascia that surrounds groups of muscle cells. Okay, groups of muscle cells are given a special name. Okay, groups of muscle cells are known as fascicles. Okay, so you might hear me talk about fascicles at some point during our remaining conversation here in chapter 10. So the epimysium covers the entire muscle. Deep to the epimysium is the paramysium. It surrounds groups of muscle fibers that we call fascicles. And then we have another layer of connective tissue, another layer of fascia that actually surrounds individual muscle cells, and it's known as endomysium. So it doesn't warp, it wraps around individual muscle cells, okay? And what is important that you appreciate with these three layers here is that the epimysium, the paramysium, and the endomysium are physically continuous with each other. Let me say that again. The epimysium, paramysium, and endomysium are physically continuous with each other. And what that means, if I could use a silly analogy for a moment, if you had a t-shirt on this weekend because it was chilly, you had a t-shirt on, you had a sweatshirt on top of your t-shirt, and then you had a jacket on. So you have a t-shirt, sweatshirt, and jacket. Now, if those three objects were physically continuous with each other, it would be though you had a seamstress stitch the t-shirt to the sweatshirt and stitch the sweatshirt to the jacket. Okay, so let me ask you this in the chat window. Hold on a sec. Here we go. If someone stitched your t-shirt to your sweatshirt to your jacket, if you pulled on the jacket, would the sweatshirt and t-shirt also move? If they were stitched together, would everything move as a group? Would everything move as a unit? Now, hopefully you can see that in fact would happen. And that's how the anatomy of your body is often organized, that one structure is literally stitched to another structure, is literally stitched to another structure. So there's this continuum, this continuity of one piece of anatomy to another piece of anatomy. Okay, so it's important that you appreciate that the epimysium, paramysium, and endomysium are physically continuous with each other. Okay. Additionally, it is important that you appreciate that the epimysium, paramysium, and endomysium actually are physically continuous with the tendon that attaches the muscle to the bone. Additionally, these three layers of fascia involving the muscle are also physically continuous with the tendon. Okay, so hopefully you can see where I'm driving at with this, is that when the muscle contracts, you're going to tug on the endomysium. And because the endomysium is attached to the paramysium, you're going to tug on the paramysium. And because the paramysium is attracted to the because the paramysium is connected to the epimysium, you're going to tug on the epimysium. And because the epimysium is connected to the tendon, you're going to tug on the tendon. And because the tendon is connected to the bone, you're going to tug on the bone and you're going to move the bone. That's what I'm trying to get you to see, that all of this anatomy is stitched together. They are separate things that we can highlight as a piece of anatomy, but they are connected to a neighboring piece of anatomy. Okay, any questions? Okay, let's continue here, folks. We have a lot to do. I can't really talk about the physiology until you're aware of these pieces of anatomy. So we need to talk about the microscopic anatomy of muscle fibers and take a look at figure 10.2 to do that. Microscopic anatomy of skeletal muscle fiber. All right. And let's see here. So, okay, I'm just going to start listing some things out here. I want you to please look at figure 10.2 as I do that. Okay. So first off, the sarcolemma. Sarcolemma is the term we use to refer to the plasma membrane of a muscle cell. Okay. Now, one thing that might be occurring to you, because I know it occurred to me when I was first introduced to this, you get to a point with all this stuff that you think, okay, so sarcolemma is the plasma membrane of this cell. Why can't I just refer to it as a plasma membrane? Why do I have to use the word sarcolemma? Well, it's a valid question and a valid point. The reality of it is, as you get more sophisticated in your background, you're going to use very precise terminology for specific pieces of anatomy. In other words, the term sarcolemma cannot appropriately be used to refer to a neuron plasma membrane or an epithelial cell plasma membrane, because the field of anatomy and science has defined the sarcolemma as a muscle cell plasma membrane, okay? So as you get more focused and more specialized, you will use more specialized terms. Yes, the sarcolemma is just the plasma membrane, but it's specifically the plasma membrane of a muscle cell. Okay. Let's continue. Next, we have the transverse tubules. Transverse tubules are also sometimes simply called T-tubules. Okay, so let me ask you a question in the chat window. Here we come. What color are the T-tubules in figure 10.2? What color are they? Do you see it there? Look at panel C as in Charlie. Look at panel C as in Charlie, figure 10.2. It's at the bottom there. Do you see it? Okay, I've got one person responding. How about the rest? Okay, one more person. Come on, folks. I got 2 people responding. There's not more than 2 of you online. Do you see it? Okay, thank you, Shay. All right, so hopefully in figure 10.2, panel C is in Charlie. At the bottom, you see the T-tubule and it is a light blue color. I have another question for you. Here we go. What color is the sarcolemma in figure 10.2? What color is the sarcolemma? Okay, how about 2 more folks? 2 more folks giving feedback. Thank you, Courtney and Shay. One more folk. Okay, Noah. All right, good. So hopefully you can see that the sarcolemma is also blue. And so I'm trying to get you to see, take really good look at the fact that the sarcolemma is blue and the T-tubule of panel C as in Charlie is blue. And in fact, you will notice that the transverse tubule, the T-tubule, is really an inward extension of the sarcolemma. It's an inward extension of the plasma membrane, and that is super, super important for understanding the electrical physiology of muscle fibers. So a T-tubule, these are invaginations of the sarcolemma. Invaginations of the sarcolemma, meaning they're inward extensions of the plasma membrane of a muscle fiber. Okay. Number 3 here, sarcoplasm. Sarcoplasm is probably what you could guess. The sarcoplasm is the muscle cytoplasm. A muscle cell cytoplasm. There's a couple things I want to draw your attention to here about the sarcoplasm. Obviously, the features of a muscle fiber probably need to be different from the features of an epithelial cell, probably need to be different from the features of a blood cell, probably need to be different from the features of an immune system cell to do very specialized tasks, right? And so the sarcoplasm, the cytoplasm of a muscle cell, is absolutely loaded up with glycogen. Okay. Glycogen, as you may recall from exam 1, is the primary storage polysaccharide, carbohydrate, for animal tissue. And so what I'm telling you is that muscle fibers are loaded with glycogen because the muscle cells need an abundance of biochemical fuel to power that contraction, right? So that you can go to the gym and you can lift, you can deadlift a 100-pound barbell or whatever it is you're trying to lift. All right, so you're going to find a lot of glycogen in your skeletal muscle fibers. You're going to find glycogen in cardiac fiber too, a little bit less than smooth fiber, but you're going to find glycogen in muscle cells in quite a lot of abundance. Additionally, there's another substance that I need to highlight for you that's unique to muscle fibers. I'm going to ask you this in the chat window. Okay. Here we go. What is hemoglobin? What does hemoglobin do in your body? Now, we haven't talked about it in our course, so I'm wondering, I'm hoping that maybe you've heard about hemoglobin in some other aspect of your life. Okay. Any takers out there? Can you fill me in on hemoglobin? Okay, Shay mentions that hemoglobin's an iron carrier. Shay, you are right in one sense. Hemoglobin will contain iron ions. That's absolutely true. And you mentioned red blood cells, Shay. So I'm going to work with what Shay's given me. If anyone else wants to contribute, feel free to do so. Hemoglobin is a substance that, because of its iron, has the ability to bind oxygen in the bloodstream and transport oxygen to the tissues of the body. You'll learn all about it in A&P2. Well, muscle cells do not contain hemoglobin. They do not contain hemoglobin, but they do contain a close chemical cousin of hemoglobin called myoglobin. Myoglobin is a chemical cousin to hemoglobin. Okay. The purpose of myoglobin is to bind oxygen and store it for release in the muscle cell when the muscle cell needs the extra oxygen to power that process that you read about in chapter 3 called cellular respiration. So myoglobin is used to store and release oxygen to muscle cells to support aerobic cellular respiration. And for those that don't remember what the purpose of aerobic cellular respiration is, the purpose of aerobic cellular respiration is to generate ATP to support muscle contraction. Okay, so there's a lot of important, complicated ideas here that we start to wrestle with in chapter 10. Okay, so the sarcoplasm of muscle cells contains biochemical fuel called glycogen, which will eventually be broken down into individual glucose molecules inside the cell to support aerobic cellular respiration. Aerobic cellular respiration is more efficient at extracting energy out of glucose when oxygen is available. And so therefore, Mother Nature has evolved a very special molecule, myoglobin, to bind oxygen and store it inside the muscle cell for when the muscle cell needs it to produce ATP to contract muscle tissue, okay? You can think of myoglobin as an oxygen storing battery. An oxygen storing battery. Okay. For those that may have any experience with electronics, myoglobin is basically a capacitor. Okay, it stores something. All right. Thoughts or questions, gang? Okay, I'm going to keep rolling here. Next, we have sarcoplasmic reticulum. Put your eyeballs on that in figure 10.2. The sarcoplasmic reticulum you can see is color-coded orange in the picture. Obviously, in the real body, these objects do not have blue and orange coloring. It's just artificial for your textbook to explain something. The sarcoplasmic reticulum is a network of membranes that surrounds objects called myofibrils, and we'll talk about them next. So the sarcoplasmic reticulum is a network of membranes. It wraps around things called myofibrils, which we haven't defined yet. The sarcoplasmic reticulum is super important because the sarcoplasmic reticulum will be used to store calcium. To store the calcium and at an appropriate time, release the calcium to trigger muscle contraction. Okay. So, if a muscle fiber was low on calcium, if it had to extract calcium out of the blood, which then had to extract calcium out of the extracellular matrix of the bone, that would just take too doggone long. It would take too long. Our bodies couldn't function correctly like that. So what Mother Nature did was Mother Nature designed a membrane that would actually store enough calcium in a typical muscle fiber so that the muscle fiber can do what it needs to do on a daily basis without worrying about drawing calcium from the extracellular matrix of bone. Okay, so sarcoplasmic reticulum stores calcium to support muscle contraction. Number 5, myofibrils. Myofibril. Okay, the myofibril, as you look at figure 10.2, take a look at the myofibril. The myofibril is known as a contractile organelle. Okay, a contractile organelle. The myofibrils go basically from one end of the cell to the other end of the cell. You can kind of look at that in a simplistic fashion if you look at figure 10.2, panel D as in David, and you see the long cylindrical myofibrils there, right? They basically go the entire width of the cell. At any rate, the myofibrils are the organelles that actually shorten, and when they shorten, because they're connected to the sarcolemma will shorten, and because the sarcolemma will be covered with these connective tissues that I defined for you about 5 minutes ago, all of those things will shorten, and eventually we pull on the bone and everything works correctly, okay? So, the myofibril is what, well, let me say it this way. When you weight train at the gym and you get stronger and your muscles get bigger, your muscles are getting bigger not because you are manufacturing more muscle cells. You don't make more muscle cells unless there's been some traumatic injury, okay? You don't make more muscle cells, generally speaking, to get stronger. You make more myofibrils. So when you go to the gym and you start a program of regimented weight training for a month, your muscles are going to be bigger than they were before you started. They're going to be bigger because you're making additional myofibrils to strengthen the muscle cell. Okay. When you weight train, you get bigger, stronger muscles by manufacturing additional myofibrils inside the muscle cells. You do not make additional muscle cells. So someone like, for my generation, Arnold Schwarzenegger, think about his big arm muscles and things, okay? He got big arm muscles because he trained and he made many, many additional myofibrils, not additional muscle cells, okay? Thoughts, questions? All right, I can see that we're out of time here. Folks, we have a lot to do on Wednesday, but we will be very methodical about it. Lecture and probably additional coverage in lab, but we will finish this chapter 10 on Wednesday, okay? So, any questions?